Alright everybody, welcome back to this mini live. Having said that, it's gonna be 30 to 35 minutes long because that much time I have, man. Alrighty, so let's be live and let's start discussing about the things, and I hope right now it's actually gonna be done. Last time I just went live for 10 minutes and it was quite quick. I didn't even have time to just explain the things properly. Right now I have. So without any further delay, let's simply get started and let's see what all we will be able to cover in this particular section. So we are going to be mainly covering the things related to scaling. So there are two types of scalings, like vertical scaling and just a sec. There was some kind of insect over my head, on my head, not even over my head. Don't know what that was. Just a sec. Alrighty, that was not the insect. That was some kind of what? Something? Or that could be an insect, I'm not sure, but never mind. Let's continue from here on. So yeah, I was just simply discussing that this particular section. So when it comes to scaling, so there are two types of scalings, vertical scaling and horizontal scaling. Vertical scaling in the sense you have a machine and you are just increasing, like that is a 8-core machine. Okay, 8-core machine in the sense one core has 2 threads, so 16 threads machine. So ultimately I can say that is a 8-core machine, and now you are increasing cores on that machine. So ultimately you are vertically scaling that. You are scaling the power of the CPU. You are scaling mainly power of the CPU and other stuff so that it can actually perform better. So you are just focusing on only one CPU. So kind of you have only one machine and you are adding more and more power to that. You are adding more cores. You are adding more powerful CPU to that particular machine. And this is how you are vertically scaling it, so that to handle more traffic, that machine becomes more powerful. So this is called vertical scaling. When it comes to horizontal scaling, it simply means that you have a machine, that's okay. Now you got a lot of traffic, so instead of increasing the size of the CPU, adding more powerful CPU, more cores, you are adding more machines. So instead of using one machine, right now you are using many. Okay, so this is called horizontal scaling, as simple as that. And again, there are some servers that actually get this job done, so don't really need to worry about that. Even I'm not aware of them, but I will be knowing them. What's the delay? Alright, so that was the thing about horizontal scaling and vertical scaling. And even if you have one machine, so just suppose I have one machine right now and I want to use all the cores of my CPU. So how am I even gonna be using that? So by default, when it comes to JavaScript, so JavaScript is a single threaded language. So if you are running a process, so that process will be running on a single thread, as simple as that. So let's even first of all talk about this particular thing that I'm actually doing over here, and after that I will be going ahead. So this is the normal function I have, say response hello world, and this simply gives me the process ID, and this actually calculates the sum. Okay. So n is gonna be the number that I will be getting from there. Count is gonna be 0 by default. If that's equals to greater than this number, then of course I will be returning this. And what does this mean? That only till this particular point I can actually calculate the value. So if n is greater than this, then n is gonna be equals to this. For let I is gonna be this much, and then final sum. Okay, got this thing too. So what actually happens over here? Mainly I'm gonna be talking about vertical scaling. And even before scaling vertically, you need to make sure that you are actually able to use all the threads available. It's not like JavaScript is a single threaded, so you are using a single thread. So that's gonna be problematic. So suppose you have 8 threads or 10 threads available and you are only using one thread at a time. So you ran a process, that process is simply using one thread. How about the remaining threads? They are just simply remaining doing nothing. So you are not using your machine to its fullest level or power. Okay, so what you can actually do, you can fork new cluster. So there is a package called cluster. I think it is natively available. Yeah, if I'm not wrong, cluster. Let me make sure whether it is available or not. Yeah, so cluster is natively available, and using cluster you can actually fork it. So you can fork many processes. So suppose there's gonna be one top level process, and that top level process will actually fork the child level processes. So parent level process will actually fork the children level processes, and that's it. The job is done. And the thing is that the top level process will actually even create the process IDs for those children. So suppose you ran a process, this process itself has a process ID, and that is actually forking the child level processes, and those child level processes are gonna be having their own process IDs. I will be even showing this particular thing, and this is how things actually go on. And let me even explain it verbally because it is quite easy to understand, so I don't really wanna spend a lot of time in this particular thing. So what actually happens over here, that this is the main file that I have over here, and inside this main file I have suppose 8 CPUs, right? So the length of the CPU array is 8, and on the basis of that thing I'm actually forking 8 arrays, 8 clusters. And forking cluster in the sense, once you actually fork a cluster, that forking runs the same file again. It's as simple as that. So if you are forking something, so that particular file will run again. So in this case I'm forking the cluster over here. That simply means this file will run as many times as I actually fork the cluster in here. And if suppose I have 8 CPUs, so this cluster will be forked 8 times. That simply means this particular file will run 8 times, but not 8 times actually. Yeah, 8 times. But let's see what happens when it actually runs. So first of all, for the first time I will run this file. Okay, kind of I can say this is gonna be running 9 times. Why 9 times? First of all, I will run this file. Okay, once I run this file, then that is 1 plus I have 8 cores. So this particular cluster, cluster will be forked 8 times. 1 plus 8 is equal to 9. So the first time simply this the first time when I just run the code, this whole code runs, and then clusters start getting forked, and that is why it will run 8 more times, because I have 8 clusters. What will happen when the clusters are forked? It's pretty simple. Whenever the cluster is forked, at that time this file run again, and then the second cluster is forked, this file will run again. And what actually happens when I run this file for the first time? At that time cluster.isPrimary is true. So whenever you are running this file for the first time, before any cluster is actually forked, okay, once there are two things: the state before the cluster is forked and the state after the cluster is forked. So when you run this file for the first time, there is no cluster forked, right? So that is why cluster.isPrimary is actually gonna be true. This is gonna be the primary file. So isPrimary is gonna be true. That simply means this particular section is run. So there are two sections. If else statement is here, and this is the if else statement I have. So cluster.isPrimary is gonna be true for the first time when there is no cluster forked, and once the cluster is actually forked, at that time the value of cluster.isPrimary is actually gonna be false. As simple as that. So the first time when I run this particular file, this is true. That simply means this runs. That simply means cluster is forked 8 times, or again you can call them cores, you can call them threads. Cores of course have 2 threads, so there are gonna be 16 threads. So but forget about that, you can call them workers. So ultimately 8 clusters are forked, 8 workers are forked, and those workers or those clusters are running on 8 threads which are available. As simple as that. So a cluster is gonna be forking 8 clusters are gonna be forked, and those 8 clusters are gonna be running on 8 cores, because those 8 cores are available, and they will be getting their own job done. As simple as that. And the next time whenever the cluster is forked, this particular whole page will run again, and as soon as the whole page runs again, the second time cluster.isPrimary is actually gonna be false. That simply means this will never run again. This part will only run once when you run the file for the first time. As soon as you run the file for the first time, a new cluster will be forked, and as soon as the new cluster is forked, this whole file will run again, but at that time the value of cluster.isPrimary is gonna be false. That simply means this particular section will run, and once this particular section is running, you are actually listening to the app, and listening to the app in the sense all the logic related to this particular app is here. That simply means you can just access these routes and just make a request to the server and all, and that's it. What is the benefit of it? The benefit is simple, that right now you have 8 clusters. Okay, sorry, you have 8 cores, and you have forked 8 clusters. So ultimately same file will run on all the threads. As simple as that. The first time when you ran the file, so it was true. So ultimately it created 8 clusters. It forked 8 clusters. It ultimately created 8 workers. Now those workers, they will simply run this file again. So 8 workers got created. That simply means this file, this whole code ran 8 times. Not only that, this particular whole code is actually running, or in simple words, those 8 workers, they are actually using all the cores available. Again, it keeps switching from one core to the another, and it just things keep happening like this. But ultimately all the cores are actually being used, and once all the cores are actually being used, So if you just send any request, so one core will handle that request, another request comes, then another core will handle that. If many requests comes, so all the cores will start just simply being used. So if there's really light work, so even one core can handle that. And not only one core, this core related stuff, it just simply keeps switching. It does not mean that only one core will handle only one request, one core. There's high probability that even this may happen, but most of the time what happens that it just keeps switching in the sense, suppose I'm running a process, that doesn't mean that that particular process will only use fork number 1 or core number 1 or core number 2. If there are 8 cores, they just keep switching in the sense, they switch so fast that of course without naked eye it's really impossible to see that, but ultimately the switching time is really very negligible. That simply means they switch, they keep getting their job done and we don't even realize, but yeah, they do switch. So ultimately you have 8 clusters, all the clusters they keep getting used once you have created the fork, once you have forked the cluster. Otherwise, if you don't fork it, that simply means your process will only use one cluster and one core, and if it is using one core, the remaining cores are gonna be just doing nothing. As simple as that. I hope you got it. Having said that, let's see, if I know more about it, I will be letting you know. But let's ask about the same thing to ChatGPT, and let's see whether it is actually able to help us better or not. So if I'm able to share the screen right now. Alrighty, so here we are. So tell me about cluster in JS and what's the flow. Okay, it knows my name, that's amazing. Sure, Vipendra. Let's understand the cluster in Node.js, very simple flow. Okay, so in Node.js by default your app runs on one CPU core only, that is right. Even if your computer or server has 4 cores, 8 cores or 16 cores, so your Node.js server uses only one core. Cluster module helps you use multiple CPU cores by creating multiple Node.js processes or workers. So it simply created multiple processes, and again those workers or those multiple processes will be created on the basis of the number of the CPUs that you have, not CPUs, the cores you have on your CPU. So if you have 8 cores, 8 processes or 8 workers are going to be created. If you have 16 cores, then 16 processes or workers are gonna be created. And not only those workers or processes, once those processes are created, you even get the process ID. This is the really important thing, that okay, by default if you run any file you get the process ID. Now that particular file, if that is actually running the same file, suppose 8 times, so though the process IDs of all those processes that ran 8 times, you will have the process ID too. I will be showing that, not a problem. So by default, can I do that right here? Suppose I am creating a test.js over here, and inside this test that I have CLG hello there, and not only that, let's forget about CLG hello there. I'm gonna be just simply writing process.pid. Okay, and let's simply run this file ls, and node is gonna be test.js. Okay, as soon as I ran it, I got this process ID. If I run it again, the process ID just keeps changing. Okay, so whenever I run any particular file, I get my process ID, right? It's as simple as that. And in case if this process itself are creating many processes, so all those many processes will have their process IDs too. So it's like you have a top level process, that top level process is actually creating many children level processes, and those child level processes will have their own process IDs. So ultimately it doesn't matter who is creating a process. If there is a process running on your CPU, running on your machine, that process, yeah, so that process will definitely have a process ID. Okay, so this is how we can just simply go ahead. By the way, you may not be able to see that I just ran a code, but again I was sharing the screen. My bad, let me share my entire screen. Right now you should be able to see that. Okay, I'm sharing my entire screen right now, and that simply means okay. So over here I just simply ran this particular code, and once I ran that, I ran it actually many times, and the more you run it, the different types of process IDs you get, and ultimately if there's a process running, you will definitely get the process ID. Okay, so let's continue with this thing. Clusters module helps you use multiple CPU course by creating multiple node.js processes or workers. Call them processes, call them workers, that's fine. Why cluster is used? Because node.js is a single threaded, one process can handle many requests, but CPU heavy work can slow it down. One process can handle many requests, but CPU heavy work can slow it down. Cluster creates multiple workers processes to distribute the load. As simple as that. If you are not using clusters, only one CPU is going to be used, and one CPU, ultimately one CPU is one, not even CPU, one core is going to be used, and if one core is being used, that means it is a single threaded language, so no doubt it can handle many requests. So requests are nothing, requests are really lightweight, right? So handling many requests isn't really a big problem. Having said that, if you really get many, it might get problematic, but most of the time, especially in development section, it's not really a big deal. Again, in production, if there's a lot of traffic, then it may even become a problematic thing. Not only that, if you are getting some CPU heavy work in the sense, suppose you are getting a video to just simply kind of process that, until suppose you have AI system learning running on your server, or kind of you are getting the video you are getting the videos, and you are just simply kind of getting the ultimately estimating the video, knowing more about the video and telling the user about the video. So when you actually know more about the video, when you kind of run the video file on your server to just know about the video, at that time CPU is going to be used. And in case if you are using only one CPU, that simply means it's gonna be really hard to just simply manage the stuff. At that time, if you have clusters, and not only clusters, if you have many clusters, and those clusters are actually using all the CPUs of your machine, all the cores of the CPU of your machine, in that case what will happen? You got a video. Right now that video will not only run only on one core, rather it will be running kind of on many CPUs, because look, at a time the process can only run on one core, but those core keep switching. So suppose core 1 is running right now the core is 2 started working, then 3, then 4, then 5, they just keep switching really fast. We can't really see that, but yeah. So this way the load is not gonna be only on one core, rather the load is gonna be on many, and this way load balancer is gonna be okay. Having said that, I do need to know more about it. It's not like I really got good command over it. I'm still learning, but it's fun to just know about this stuff too. Okay, let's continue. More workers, more performance, more request handled. So ultimately there are more workers in the sense more processes are running. More processes can run when you actually fork the cluster, and when you fork the cluster, at that time they are gonna be using different cores, different threads. Ultimately not only one single thread will not be used, rather multiple threads are gonna be used, and this way multiple threads are being used kind of, and cores keep switching. So this is another thing. And the second thing is that as there are more processes running the same code, so once the request comes, any process can handle that, and once any process is handling that, any core will handle that. The process will actually run on any core depending on which one is free, and even it keeps switching, and that simply means it will be able to handle the request easily. What is a worker in cluster? A worker is basically a separate Node.js process, runs the same server code, has its own memory and event loop. Example, if you have 8 cores, you create 8 workers, then 8 node processes will run, each can handle requests. So ultimately 8 processes are node processes or node workers are running, they can handle the request too. And cluster flow, how it works internally, step by step. Master process starts master process starts in the sense primary process starts. That simply means you ran the file for the first time. When you run node.server.js, ultimately this time we are actually running node.bin.js. So whenever I run this particular file, at that time it actually starts, and in this case the name of the file is server.js. That's another case, but yeah, this is how we can just simply go ahead. Master forks workers. So ultimately the workers are actually forked. Cluster is forked, or whenever the cluster is forked, the new workers are created. So I can say workers are forked or new processes are forked. Each fork creates a new worker process. As I said earlier, whenever cluster is forked, a new worker is created. So new worker is created in the sense a new worker process is created. And example, if CPU cores is equal to 8, then master creates 8 workers. Again, this actually depends on your code, the kind of loop you have. Right now I'm actually creating 8 folks over here because I have 8 CPUs. It depends on you how many folks you actually want to create. Let's continue. And workers start server. Each worker runs the same file again. That's what I was saying, that once a fork is created or worker is created or a process is created, that process will run the same code again. So ultimately, as soon as I forked it here, this will run again. Then I forked it here, this will run again. And when it runs again, at that time cluster.isPrimary actually becomes false. That means this particular section will be running. That simply means now the same app, the same code related to app is actually running on 8 processes, 8 workers are actually handling them. And not only that, 8 workers are handling them. That means 8 processes are running. There are 8 process IDs and they are using all the cores, though they keep switching, but they do use. Each worker runs the same file again, but now in worker mode. So worker do app.listen 3000, load balancing happens. Now when request comes, load localhost, master process distributes request to workers. So request goes like client request, master process receives it, master gives it to worker 1, worker 2, worker 3, worker processes it and sends a response. This is called load balancing. So load balancing in the sense one core is not handling everything, rather there are many workers, many cores are being used at the same time. And once a request comes, if one worker can handle it well, if cannot, it will be distributed among many workers, and this is gonna be called load balancing. Node.js, Node uses round robin scheduling in most OS. Well, I'm not aware of it, but hope I will be knowing more about it in future. Round robin scheduling. Okay, let's go ahead. Full cluster example code. Again, it is actually forking it, so that's great. So cluster.it is almost the same, don't you think so? Yeah, it is actually the same. It is actually forking it. Have I even given it the code that I had, or I just simply asked? It turns out I just simply asked it and it just generated the code on its own, and it is just similar to ours, right? So in our case, if I'm not wrong, we are using import statement, yeah, and it is actually using common.js. So we are actually using EJS right now. But yeah, cluster master process running PID. So master process will have its own PID because that is of course a process, and there are gonna be child processes. And that's it. Exit starting cluster.fork, express handle, and that's it. Nothing. One more thing. Client request master worker 1, worker 2. Important note, cluster is best for web servers handling many requests using all CPU cores. Cluster is not useful for database bottlenecks, so show slow API from third-party CPU heavy task inside a single request. For that use workers. For that use workers threads. Well, need to know more about it. Okay, cluster versus worker threads. Cluster threads versus worker threads. Okay, cluster multiple processes, multiple threads. Separate memory, shared memory possible. Web server scaling, CPU heavy tasks. Slightly slower IPC overhead, faster for CPU. Wow. Okay, well, I'm not aware of threads at all. It's like I know if there is a CPU, that CPU has 8 cores and each core will have 2 threads, so ultimately 16 threads are gonna be there. I do need to work on my computer fundamental stuff, but okay, not really have a lot of time for that. I still have to work on that, but I'll be knowing more about it. Real life example at CPU cores, 1000 users hitting your server without a cluster, one process handles all, server becomes slow. With the cluster, 8 workers handle request, load is divided, server becomes fast. Yeah, that's what I was saying. One more thing, if there are more than one worker, will those workers be using same code, or it keeps switching? That's what I've been actually telling you since the beginning, but let's see whether it actually switch or not. Great question. If there are multiple workers, do they use the same core? No, ideally they will not use the same core, and that's what I've been saying, that they keep switching. When you create multiple workers or processes, the operating system OS schedules them on different CPU cores, schedules them, because on one core only one worker can run at a time. If another worker needs to run, that simply needs to wait if another worker is already running, and then the work will get done. What actually happens? Workers less than equals to CPU cores. If workers are less than or equals to, then we don't really have any problem. 8 workers will be running on 8 cores. Then mostly worker 1 runs on core 1, worker 2 core 2, worker 3, and so on. One thing, when I was in my class 11th and 12th, my teacher used to say so on and so forth. At that time I was kind of learning English, so I used to just say, oh, like, what is this so on and so forth? It simply means that it just keeps going on like this. It's obvious, or so on and so forth. The examples are gonna be just like mentioned above, as simple as that. Okay, by the way, let's continue. If workers are greater than, then the problem actually occurs. So suppose I have 8 CPUs, 8 cores, and I have 16 workers. Now workers must share cores. Okay, so one more thing. So far I had 8 cores because I have a CPU. That CPU has 8 cores. That simply means I only created 8 workers. That's it. I forked the cluster 8 times. I could have forked the cluster 16 times. And if the number of workers is actually equals to the number of cores of the CPUs, cores of the CPU that of my device or machine, in that case I don't really need to worry about it. I mean, worker 1 will be running on core 1, worker 2 core 2, worker 3 core 3. This is how it will keep going on. If the number of workers is greater than that, then we do need to worry about it, and rather it will handle it. So now workers must share cores. If workers are actually greater than, run worker 1 on core 1 for some milliseconds. That's it. Then switch to worker 9 on core 1. Then switch again. It does not need to be worker 9 actually. The worker can be any. Again, randomly happens. Whichever worker actually has the job to do, whichever worker is actually scheduled, that worker will be used. As simple as that. This is called context switching. So all the workers, forget about the workers, the cores, they keep switching. The context keeps switching for the workers as per the need. If there are more workers and there are less cores. What does it mean? It simply means that suppose you are uploading a video on YouTube. Okay, YouTube has the YouTube infrastructure. The company itself has some limited resources. It's not like it has unlimited resources, right? So it has some limited resources. That simply means limited CPU power. Again, it is a company. It is a big level company, multi-billion company. Okay, forget about that. But ultimately it doesn't matter how much infrastructure it has. That infrastructure is gonna be at the end limited, right? It cannot be unlimited. And when it is a limited machine capacity it has, that simply means if it is actually getting lots of requests, so ultimately lots of workers are definitely running. But if there are many requests, that simply means that's gonna be problematic. And having said that, if you are actually uploading a video, so one worker will come and start uploading your video, start processing your video. When the worker is actually processing the video, at that time you can't even context switch, because the worker is actually busy processing your video, right? So if the worker actually context switches, if the suppose this worker was using this particular core, worker 1 was using core 1, and that worker 1 is actually processing your video. So right now it cannot switch the context directly. First of all, it needs to get the job done, right? And once the job is actually done, then the core is actually going to be free. And once the core is actually free, after that you can actually that core can be given to some other worker. But let's even talk about this. If I am uploading a video on YouTube, then a worker will process that. Will the context switching happen while processing the video? let's even talk about this thing. Context switching can happen while processing the video upload, but let's understand it correctly. Very important concept. Okay, when uploading video to YouTube, what happens? Uploading video is mostly input output task, network plus file plus reading, not CPU heavy. So worker is mostly reading video file in chunks, sending chunks to YouTube server, waiting for response. During waiting time, CPU is free. Okay, CPU is free. I'm not even talking about that, not just uploading the video, rather processing the video. Okay, never mind. So OS can easily run other workers only when the CPU is actually free. If there is a worker that is consistently running the same, processing the same video, that means CPU is not going to be free. And if it is not free, then you know what will happen. But let's go ahead. Will context switching happen during upload? Yes, during upload, because OS CPU always switches between processes. It is not a problem because, okay, what exactly happens? Okay, this is what I actually wanted to say. I said in video processing, it should be like video encoding. When video encoding happens, at that time the worker needs to be busy encoding the video, right? So when context switching becomes serious, context switching becomes heavy when CPU heavy process is happening. For example, video encoding, compression, thumbnail generation, encryption, FFmpeg processing. In that case, worker 1 is continuously using CPU, then OS may switch it with the other workers. Slow down. Possible. Fine answer. Yes, tell me more about it, bro. Bhai, I was about to say. Okay. Tell me more about it. Does it mean once the encoding is done, context switching will happen? Just as simple as that. Yes, you are thinking in a correct direction, but one small correction. Context switching can happen both while encoding is happening and after encoding is done. It's not like encoding finished, then switching starts. Let me explain. What happens during encoding? When encoding starts, example using FFmpeg, CPU is working continuously, that's right. Worker process is running heavy computation. Core use becomes near 100%, that's right. Now, OS will do this. OS is scheduling during encoding. Even if worker 1 is encoding, OS will still give CPU time to worker 2, worker 3, Chrome, system services. So OS does small switching like worker 1 encoding 10 millisecond, worker 2 2 millisecond, worker 3 2 millisecond, okay, 3 1, worker 1 again 10 millisecond. Okay. This switching happens constantly. That switching is called context switching. Does encoding stop because of the context switching? No, encoding does not stop permanently. But yes, it pauses for microseconds or milliseconds and then continues. I thought once the encoding is stopped, then it stopped. But if it is paused, it can just continue from there on. So encoding still completes, but slightly slower if many switches happen. Yeah, that's right. After encoding is done, what happens? Once encoding is done, the worker becomes free. Now it will mostly do sending file upload, waiting for the response input. Now CPU becomes slow, so OS switching still happens, but it becomes very cheap. Yeah, that's right. Main rule, very important. Context switching is always happen in multitasking OS, but the real issue is context switching becomes expensive only when CPU is fully busy. Simple example. Okay, I think I've gone through enough examples right now. The thing is simple. That doesn't matter if you are getting many requests or if you are actually doing CPU heavy work. Context switching will definitely happen. The only difference is context switching in the sense, first of all, worker 1 will be using core 1, then for some milliseconds worker 1 will be using core 2, core 3, core 4, and this is how it just keeps going on here and there, and just simply balancing the load. But having said that, core switching, context switching will definitely happen. It's all about when your CPU, your machine, your worker has a lot of heavy work. At that time, context switching gets expensive, and otherwise in the remaining time it gets really cheap. Like if it is actually free, then you can easily switch the context. But if it is busy, then switching context will definitely happen for load balancing, but it gets expensive in the sense it is actually handling more stuff, right? So when you actually switch the context, that simply means you are actually using another code, and that code will have to just handle that much load. That simply means becomes expensive or something. Let's ask about this thing as well. How does it become expensive when encoding? Let's see. Great question. This is a real core concept of CPU scheduling. Why context switching becomes expensive during encoding? Because encoding is a CPU heavy, meaning the CPU is continuously doing a calculations, no waiting. So if OS, wow, amazing. I'll actually have to go to my fields, but let's get it done. Because the encoding is the CPU, okay, come on, the CPU continuously doing calculations, no waiting. So if OS interrupts the encoding process again and again, it creates extra overhead. What happens in the context switching? When it switches from worker 1 to worker 2, it must save worker 1's state. So OS has to save CPU registers, program counter where it stopped, memory mapping, thread process info, then load workers to saved state, then saving load takes time, loading takes time. That time is called overhead. Why is this overhead a problem during encoding? Because encoding needs CPU non-stop. Encoding wants to CPU like encoding wants CPU like, but because of context switching, CPU becomes CPU time becomes like this, where 0 means CPU is wasting time switching. So encoding becomes slower. Cache problem, most important region, the biggest region. CPU has something called CPU cache, L1, L2, L3. Cache stores frequently used data, so CPU can access it super fast. In coding, it uses a lot of repeated calculations, so cache becomes very useful. Now what happens during context switching? When OS switches to another worker, cache gets filled with workers 2's data. Worker 1's data cache is removed. Now then worker 1 comes back, cache is cold, empty for worker 1. CPU must reload everything from RAM again. RAM is used for running the processes whenever you just turn the machines on. So if you are actually running some game and all, mostly RAM doesn't store anything, it just simply helps you run the processes. So and RAM is much slower than cache. This is called a cache miss. Performance drop. So context switching causes overhead time saving, loading CPU state. Cache miss, CPU loses fast cache, the encoding data, pipeline disruption. Modern CPUs optimizing instructions flow, switching breaks that. Simple real life analogy. Okay, I got that. Ultimately what the thing is that context switch happens, and whenever the context switch happens, the first thing is that overhead in the sense core worker 1 is handling the encoding, suppose, and core 1 is being used, and the core 1 actually caches the stuff as well. And now you are switching to core number 2. So when you are actually switching to the switching actually creates some extra work for the worker or the core, and that actually disrupts the whole pipeline. Normal encoding was happening, suddenly you are switching the code. So ultimately overhead is gonna be there, extra process is gonna be there, extra work is going to be there. Apart from that thing, your core actually caches the some process related stuff, and when you are actually switching to the core 2, that core 2 has no idea about the cache of the first core. That simply means again that is going to be problem. Then it will have to use the RAM, get the information about the current process, and then it will have to process the things and all. So yeah, it is like that, and wow, that's amazing. So but it does happen again. Well, it does cause some problems. It gets overhead problem, then cache miss problem, but ultimately it does balance it, right? Your one core cannot handle it. It's better to give, if you have a lot of work, better to give it many cores so that they can handle it little by little. So it's kind of load balancing does happen, but with some extra effort. It's not like it comes for free. If you wanna get something, you will have to lose something. So yeah, cache miss, overhead, you have to just compromise these things for your load balancing stuff, and this is how it actually happens. So that was it for now. I'm gonna be catching up soon, like after 20 minutes, not 20 minutes, 10 to 15 minutes. I'm supposed to be back, and then I'm gonna be live again for 30 to 35 minutes, something like that. I'm gonna be catching up soon. Take care and see you.